Hello, thank you very much for listening to this presentation. My name is Hao. I'm a senior studying mechanical engineering and computer science. This work is done in collaboration with Professor Barton, Dr. Moyne, Dr. Kamsey, and I want to thank their guidance and support along the way. This project is done in part to fulfill the Capstone requirement for the College of Engineering honors program at the University of Michigan. And the name of this project is called Merging Subject Matter Expertise and Deep Convolutional Neural Network for State-Based Online Machine Part Interaction Classification. So machine part interaction, as its name suggests, is the interaction between machine and the workpiece. So we're going to take a look at this example. So there are two interactions in this example. One is no interaction, which is GOS1, and drilling, which is GOS2. This video shows the ideal performance of the system. And as soon as the drill bit contacts the workpiece, we can see that the interaction changed from no interaction to drilling. And as soon as it's done drilling, the interaction switch back to no interaction. So the system in this video is actually done using a threshold-based method, which is really sensitive to changing condition. That's why it's so quick to respond, but this is not ideal for practical application because it's sensitive to operation condition and it doesn't scale well. So what the system should do is to tell us how the machine is interacting with the workpiece in real time for a given time instance. So why do we need machine part interaction classification? So the first reason is that it is a critical capability of cyber-physical system, which is the integration of physical assets with computing and communication technologies. And cyber-physical system is an enabler of Industrial 4.0, the next manufacturing paradigm. And next, machine part interaction can actually be used to address other manufacturing problems such as fault detection, equipment performance analysis, etc. So this piece of information of how the machine interacting with the workpiece is very important for monitoring, planning, coordination on the factory floor. So the contribution of this project, the first one is, so we'll provide a framework for online machine part interaction classification. So this framework would deal with steady state classification as well as transition detection. And the architecture is very efficient thanks to the compact data representation. And the compactness of, or the efficiency of the architecture is very important because this is for online application. So everything we want the system to be responsive and have the prediction in real time very quickly. And the second contribution is we integrate subject matter expertise with data-driven approach. The most significant subject matter expert contribution is the error checking mechanism. We model the system or the machine as a finite state machine and use that to perform error checking. And we also describe how subject matter expertise is incorporated into our framework, and this will help others to adapt our framework to different machines and different manufacturing systems. So let's dive into our methodology. So there are three main components in our framework. The first one is the signal processing unit, and the second one is the classification unit. And lastly, we have the decision coordinator, which performs error checking mainly. So now let's take a look at the signal processing unit first. So there are two major functions of the signal processing unit. The first one is segment the time series signals input. And the second one is perform denoising operation. So since because the time series signals are streamed in real time as the sensor in the machine collect data, so we need to segment the signal so that we can basically figure out what the machine is doing at a certain time instance. And the technique we use to segment the time series signal is called the sliding window technique, which we have an illustration on the right. So what it does is to slide a fixed length window across the signal, and the data points of the signal contained in the window are collectively called a frame. And there are two parameters we can tune using this technique. The first one is the window size, and the second one is overlap. The window size determines how many data points are incorporated in a frame, and the overlap determines how many data points the consecutive windows would overlap by. And generally speaking, a larger window size would lead to better classification performance because more contexts are incorporated. And for last, we have the denoising operation, which is helpful because it's basically facilitate better performance on classification models. And next up, we have the classification units. On the left of the screen, we can see the schematic, and this might be a bit confusing, but I'll try my best to make the architecture make sense to you. Now let's take a look at the input of the classification units. So it takes in n frames. Just as a reminder, a frame is just all the data points that are included in a window, and each frame has k signals, and each signal is length w, and the length of each signal is determined by the window size. So we have an input tensor of size n by k by w. So we utilize an encoder classifier structure, and so one convolutional neural network would encode inputs into some intermediate representation, and the other convolutional neural network would classify based on the intermediate representation and output either the steady state or the transition happening at a given time instance. So now let's take a look at the encoder. So it encodes each frame into a p steady state score. So why would we encode a frame into steady state scores, you might ask? The reason is that a trajectory of how steady state score change can provide hints on when a transition occurs. So what we are effectively doing here is to encode n frames to approximate the trajectory of the steady state score. More concretely, for example, if a machine is the machine that we're monitoring have 10 machine part interactions, aka 10 steady states, then in this case, P would be 10. So we would do a 10 class scores based on all those steady state classes. Now let's move on to the classifier. The classifier would then classify the output from the upstream CNN or the encoder. The downstream CNN or the classifier would classify the intermediate representation, which is the P class steady state class score, into either into a label, which is either a steady state or the transition that is happening at the moment. And next we'll go to our final component, which is the decision coordinator. Please allow me to motivate this component because this component is generally not included in a data-driven framework. So the first motivation is that the input to the system are not independent and identically distributed. In other words, they are not generated from a stochastic process. In fact, they're deterministic because machine operations are predefined in G code. And as a result, the current state depends on the past, and we cannot treat each sample as if they're irrelevant to each other. However, feed-forward neural network do not retain memory. As soon as it's done classifying, the sample is out of window and it treats the next sample as a completely new sample. And we don't want this kind of behavior, and we want our framework to be able to memorize for a certain time span the previous state of the machine. So we'll model the machine as a finite state machine, which will perform error checking on the output of the classification units. And we'll explain a little bit more about this in our case study. For our case study, we are using the NASA dataset, the NASA milling dataset, primarily because we were not able to go into the lab and collect data due to the pandemic. And the dataset features 167 milling trials of 13 different operation conditions. A typical DC spindle current signal is presented on the right. And each individual signal consists of 4 steady states: no interaction, entry, constant milling, and exit. And there are 3 transitions between those steady states, and they are indicated in the rectangles. At a high level, we want a system to tell us how the machine is interacting with the workpiece. This is equivalent to partitioning the signal into 4 steady states based on their machine part interaction. Right? Performance. So the architecture details are shown on the left. It features a just very conventional convolution layer, pooling layer, and activation. And then we do the whole thing repeat like a sandwich. And at the end, we have a fully connected layer. So it's a pretty conventional architecture here. And the key here is the number of parameters of this framework in total. It has less than 520,000 parameters, which is very small in the modern standard. Of course, that's partially due to the fact that we're only processing one time series signal and each window is relatively small. But the intermediate, the efficient intermediate representation does help in limiting the number of parameters in our neural network. And the performance metrics on the 4 steady states and 3 transition classes are shown on the right. The framework has a decent performance on all classes except for the transition between entry and constant milling. And this is partially because the transition is more gradual and takes more data points to develop. And overall, the result is promising because the network is trained and tested on samples that are taken from signals generated from different operation conditions, which means that our network is able to pick up meaningful features of samples and classify them correctly. Previously, what we are testing are the capability of mainly the classification units because each sample are independent and different classification have nothing to do with each other. Now I want to see how well the system actually work in real time. So we stream the time series signal as if it is done in real time. And we measure the performance of the system by the delay when in detecting transitions. This is the delay from our proposed framework. We also implement a system that mimics the state-of-the-art solution, which only performs steady state classification. So we ignore the intermittent misclassifications around the state boundary and assign transitions when steady state switches. We can see our proposed framework offer a fairly large improvement in terms of delays in transition detection, plus the error checking mechanism helps reduce the number of the intermittent misclassifications and improve the robustness of the system. As the title of this project suggests, that we're merging subject matter expertise into our framework. And now let's talk about why we do that and how we do that. Subject matter experts provide inputs in 3 different aspects into our framework, which for each individual component in our framework. The first one is they decide which signal to use and what parameter of the window length and overlap. In the age of deep learning, feature engineering seems to be less relevant, and people tend to think that we don't need subject matter experts anymore. But subject matter experts are still very much relevant, we think. And the second one is that subject matter experts provide inputs into the detailed architecture and hyperparameter selections. They are most likely going to be the machine learning engineers. And lastly, and also the most important input is on how to model the machine. This is critical for error checking. A well-defined model can greatly reduce the misclassification made by a data-driven model, such as neural network. In mission-critical tasks and high-stakes scenarios, a slight mistake can be very costly, and we want a system to be as robust as possible. Okay. And for the future work, so these are the things that we want to do but didn't have time to do because paper deadlines are real and they're always feel like days away. So these are some future directions that we could take. The first one is we can potentially improve the delays in transition detection. This is very much important because everything is in real time and we want the system to be as responsive as possible. So we want them to be very sharp, very quick in response. And next one is we can have try different modeling formalism on how we model the system, how we model the machine to improve the error checking capability of our framework. Lastly, we can use a recurrent neural network to encode the time dependency so we don't have to rely on the convolutional neural network. We can try other kinds of neural network or other kind of machine learning techniques. Thank you very much for listening. And this is the presentation for my capstone design project. Thank you.